Suppose you have a bottle with a stopper. Air at 10 degrees centigrade and at 1 atmosphere is inside the bottle. The stopper has a 2 centimeter diameter and the stopper mass is 20 grams. Now suppose that the stoppered bottle is immersed in boiling water and that the cork ejects. A. What is the pressure just before the stopper ejects? B. What is the friction acting on the stopper? C. If stopper diameter is doubled, what is required water temperature for stopper ejection? Okay, A, first of all, since there is a fixed amount of gas inside the bottle, the ideal gas law tells us that the ratio of PV divided by T is going to be the same. P1V1 over T1 equals P2V2 over T2. Solving for P2, P2 is equal to P1V1 divided by T1 times T2 over V2. The volume just before ejection hasn't changed, so the two volumes cancel, and the pressure is then the initial pressure, atmospheric, 1.01 times 10 to the 5th, times the final temperature, which is 373 Kelvin, divided by the initial temperature of the bottle inside 283, which is 1.33 times 10 to the 5th Pascal. Okay, B, in order to answer B, let's do a free body diagram of the cork. And the free body diagram of the cork shows that we have a mg for the cork. The weight is down. Frictional force is downward if the cork is attempting to move up. The pressure of the air outside, P1A, down. And then inside the bottle, there is a pressure up, P2 times A. And so these forces are all in equilibrium just before the cork starts moving. That means that the frictional force plus the downward force due to the atmosphere plus the weight of the cork is equal to the upward force from within the bottle, P2 times A. We can calculate the area as pi over 4 times the diameter squared. Diameter is 2 centimeters, which is 2 times 10 to the minus 2 meters, and so should be a squared right here. And so this is 3.14 times 10 to the minus 4. And the friction is then P2 minus P1 times A minus mg, which is 1.33 times 10 to the 5th Pascal minus 1.01 times 10 to the 5th Pascal times this cork area, 3.14 times 10 to the minus 4 square meters, minus the weight of the cork, 20 grams, 20 times 10 to the minus 3 kilograms, times the acceleration of gravity. I'm just using 10 here. And so that computes out to be 10 newtons minus 0.2, which is 9.8. And so we'll just round that off and say 10. 10 newtons for the frictional force, and acknowledge that the weight of the cork has a fairly minimal effect. In part C now, it is asking what happens if the stopper diameter is doubled. Well, doubling the stopper diameter is going to cause a quadrupling of area, and if the area is bigger, there is going to be a bigger differential force between P1A and P2A. So one would expect that a lower temperature is required and a lower pressure P2 is required inside the bottle to eject the cork. So using the same free body diagram as before and ignoring the weight of the cork, P2A is equal to S sub F plus P1A. P2 is then equal to the frictional force, which will remain the same, divided by the area plus P1. And so that's going to be 10 newtons divided by this quadrupled area plus the initial pressure, 10 to the 5th, 1.01 times 10 to the 5th Pascal, that's atmospheric, and that comes out to be 1.09 times 10 to the 5th Pascal. Now we can solve for the pressure. Again, using the fact that the number of moles of gas inside the bottle hasn't changed. And so T2 is then P2V2 over P1V1 times T1. Volume, again, hasn't changed. The cork is just about to move, so the volumes cancel, and the temperature required of the water is the ratio of the two pressures, 1.09 to 1.01, times the initial temperature of the air, 283, and that comes out to 305.